This video is the makeup video for anyone who missed the special Polar Graphs Exploration Day. So what we're going to do today that's a little bit different than what we've done in the past is we're only going to work with these equations in polar. We're not going to be converting them back and forth between rectangular and polar form. We're only going to be talking about these in terms of polar form. However, to cheat and get the values that we're going to plug into the table so that we can graph it in polar form, we're actually going to do like the rectangular version of this same equation. So if you guys recall, when we did the conversions, we knew that x was r cos theta and y is r sine theta and all of that stuff. We're not going to do those substitutions. We're not going to plug anything in. So when we did this in class, I assigned one equation per group, and then we kind of compared. So for us, we're going to go ahead and we're going to graph the first one, and then I'll go ahead and show you pictures of what the other groups got, so you guys can have the benefit of seeing everything. So this is our goal. We're going to be graphing this in polar, but to do that, to cheat and fill out the table in a way that's easier for us, we're going to go ahead and graph the equation y equals 2 plus 2 cos x, because we know how to graph that. And typically we didn't see it written like this. We usually would see this number on the end of the equation. So it'd be 2 cos x plus 2, which means that our amplitude is 2. Since this is just plain old x right here, that would mean that the period of the graph is going to be 2 pi. It's not changing at all. And then this right here is a vertical shift of 2, so it goes up 2. So I'm going to go ahead and start sketching my cos graph. Since I know I have an amplitude of 2 and I'm about to shift 2 up, that means the amplitude of 2 means that my graph should go to -2 and +2. But since I'm shifting it 2 up, then I'm going to need it to go all the way up to +4. So I'm going to say 4, 2, that makes this the 0, and then -2 down there. And then I usually like to do 4 boxes for pi, just because I think that's a pretty easy graph to make. So if you guys recall, cos graphs usually start up at 1 and end at 1, and they hit -1, or sorry, I'm not pointing to 1, I'm pointing to 2. Start at 1, end at 1, hit -1 in the middle. So since this one has an amplitude of 2, we're going to start at 2, end at 2, hit -2 in the middle. And then between those, it would cross through 0. So I'm not doing the +2 part, I'm just doing the 2 cos x part. And then I can go ahead and shift all of my points up 2. So shift, shift, shift. And for these graphs, it's important that you do a really good job of drawing nice curves here. It should look very symmetrical, and that's because we are going to be pulling points from this graph and putting them in this table. So what I'm going to do now is I've got, for the angle, the x values down here, you can see that these are the angles, so these are going to become our thetas. And then the y value is actually going to become our r, because that's where it was in the equation. So the x value is the theta value, the y value is the r value. So when theta equals 0, the radius is 4. So if this is where pi halves is, then pi fourths would be like 3.5-ish. And pi halves would be 2. And 3 pi fourths would be 0.4-ish. And then pi would be 0. And then it's just symmetrical from there, so 0.4 and 2 and 3. Well, over here it doesn't quite look like 3.5. I guess I can do more like 3.6 or 3.7. And then 4. So our graph is not going to be perfect because it's kind of dependent on how you drew it, but you get the idea. Okay, so there is our cheating version of how to get the points on the table, and now we're going to go ahead and graph it in on the polar graph. I can't talk and fill this out at the same time. Okay, so I'm just writing some of my angles on here to make my life easier when I fill this out. Plotting the points. Okay. So when our degree, or sorry, our radian is 0, the radius is 4. So this is the 0 line, and then count 1, 2, 3, 4. At pi fourths, we're at 3.7. So pi fourths is 1, 2, 3. At pi halves, we'll be at 2, 1, 2. At 3 pi fourths, we'd be at 0.4. And then at pi, we hit 0. So if you guys can see, we just got points that went in this kind of curve shape. So I'm going to be real careful as I draw this to make a nice little curve, like so. There we go. And I'm sorry, the pencil is kind of reflected. I don't know if you can see that very well. And then on the other side, it's symmetric, so it's just going to do the same thing, but going the other direction. So at 5 pi fourths, it goes out to 0.4, and then at 3 pi halves, it goes out to 2, and then at 7 pi fourths, it goes out to 3.7, and then at 2 pi, it ends back at 4. So I'm going to go ahead and follow that curve. Ooh. Okay, that's pretty good. So what I want you to notice is it divots in to hit 0. The furthest out that it goes is 4. And we're crossing over here at 2. These are kind of important things I'm going to point out in a bunch of the different drawings. So again, when we did it in class, everyone had one of these types of equations. So what we did next is I picked a person from a couple different groups to have them show their graphs so that we could notice things that were similar and things that were different. So I have a lot of them on here, as you can see. So this graph, if you notice, is just like our equation that we just did. It just has a minus instead. So you'll notice it still hits 0. It still crosses this at 2. It still goes all the way out to 4, but it goes left instead of right. If we look at this next one, this is going to be similar to the one before, because this was 2 minus 2 cos theta. This is 3 minus 3 cos theta. This one, it goes into 0, but this time, instead of going out to 2, like this one does, it goes out to 3. And then when we look at how big it is, it goes all the way out to 6 over here. All right? So what we're actually going to do, I'll explain the next part of the packet. When it says sketch some of the graphs that you see from the other groups, what I would like you to do is pause the video periodically, and one of your graphs should go left, one should go right, one should go up, one should go down. And so you're going to draw a little sketch for all 4 of these, and underneath you're going to write an equation for each one. All right, so that's, as I'm explaining these, at some point pause the video and draw a little sketch of that graph. Okay, so if we compare, you guys can see that these two are similar. So this is the plus version, 3 minus 3 cos theta. Up here we have 3 plus 3 cos theta. Again, it goes in towards 0. It crosses up here at 3 and then down here at -3, and then it goes all the way out to 6. So we should be noticing some similarities there. Now if we start looking at some of the sine graphs, this one is 2 plus 2 sine theta. So you'll notice, just like our graph, it bumps in and hits 0. It goes out to 2 on either side, and it goes up to 4 right here. So this is the plus version of the sine graph. With the 2's, if we look up here, we have the plus version of the sine graph, but with the 3's. So it goes out to 3 and out to 3. It divots in and hits 0 right there. Goes all the way out to 6. All right, and then if you'll notice here, when we have the negative version of the sine graph, I'm going to see for the 2, it bumps out to 2 right here, and then it goes all the way to 4. Okay, so at this point you should be noticing some things. So the name of these graphs are cardioids. There is a pretty good chance that I'm going to pronounce some of the names wrong, so don't judge. I can spell them correctly, that's about it. Okay, so you should be writing down one for each of those. And then there's questions down there, so it's asking what determines how big the cardioid is, what determines which direction the cardioid goes. So if you're looking at what determines how big the cardioid is, you've probably noticed that the numbers, the ones that had 2s, were smaller than the ones that had 3s. And hopefully after I pointed out the same thing over and over, you noticed that if it had 2s, then the 2 and the 2 kind of determined how far it went out here. And then 2 plus 2 was 4, and that's how we knew it went out this far. All right? Or in the other case, 3 plus 3 was 6, and that's how we determined how far it went out. And if you were to look back at your graphs, it kind of makes sense that it's doing that the numbers added together would determine how far out it goes, because if we talk about having an amplitude of 2 and then shifting up 2 from that, then the furthest the graph goes up, which in this case is the radius, is 4. So it would make sense that the amplitude plus the vertical shift would tell you how far away you're going to get. All right? So those are the things you should be noticing. We also were going to talk about what determines which direction the cardioid goes. So we had some that were left and right and some that were up and down. And you should have been noticing that the cos graphs are the ones that go left and right. The sine graphs are the ones that go up and down. And that positive and negative had an effect on that as well. So I kind of already spelled out the answers for you, but I'm not going to tell you what to write here. I want you to pause the video and answer the question yourself. Okay. The next graph, sorry, getting my notes all in order. We're going to go ahead and just pretend that we're group 1 this entire time. So we're going to do r equals 2 plus 1 cos theta this time. So I'm going to grab my graph paper and I'm going to do y equals 1 cos theta plus 2. And so on this one I know my amplitude is just 1, but I'm going to be shifting it up 2 vertically, which means that I'm going to need it to go up to 3. So I'm going up to 3. Got 1, 2, 3, 4 for pi. Okay, so a normal cos graph would start at 1 and end at 1 and hit -1 in the very middle, and then between these two it would cross 0, and between these two it would cross at 0 as well. And then in the case of this graph, we are shifting every point up 2. So up 2, up 2, and then I'm being careful to draw a nice curve here. Alright, so there I've got enough points that I can kind of fill out the table now. There's pi halves. Okay, so 0 is up at 3, pi fourths, well for me I drew it so it looks like it's at 3. Over here it looks like it's at like 2.8, 2.7, I'll go ahead and say 2.8. At pi halves it's at 2, at 3 pi fourths it's a little over 1, I'm going to go ahead and say 1.2. At pi it hits 1. At 5 pi fourths, it's going to be that 1.2 again. 3 pi halves is 2, 2.8, 3. Okay, so at 0, we've got 1, 2, 3. At pi fourths, we've got 1, 2, 2.8. At pi halves, we've got 2. At this point, you should maybe be noticing this is very similar to the one that we just did, which is good, makes it easier to remember. So at 3 pi fourths, we're at 1.2, and then at pi, we're at 1. So you'll notice that we just hit a spot that's a little bit different than the cardioid we just did. At this point, the cardioid would have dipped into 0. Ours did not dip into 0. Ours is staying out at 1. So I'm going to go ahead and start drawing this curve. Alright, and then at 5 pi fourths, we've got 1.2. At 3 pi halves, we've got 2. 7 pi fourths, 2.8, and then back to 3. Okay, so let's look at some other graphs of these so that we can make some comparisons here. So again, you're going to be drawing 4 different pictures, one left, one right, one up, one down, and writing the equations underneath so you can keep track of what you're doing. Okay, so here is the other version of the one that we did, so with a minus instead, and I'm sure none of us are surprised it goes left because it would make sense that that pattern still follows what we did with the cardioid. Now if you look at like this one that we did right here, so here's the numbers we've got, you'll notice that this one again, it kind of dips in at 1 there. It doesn't go to 0 like the cardioid did, it just goes to 1. Out here we can see that it goes out to 3 and to 3, and then out here the furthest it goes is to 5. So let's compare that with the one that we did. Ours went out to 2 and to 2, it dipped in at 1, and then ours went out to 3. So think about the numbers you're seeing, think about what that possibly means. Okay, and then let's look at another one. So here we've got the 2 plus 1 sine theta. So this one, we've got crossing at 2 over here, crossing at 2 over here, and going up to 3 right there. And then again, it just dips in at 1. This one dips in at 1. So I'm going to go ahead and maybe make it so some of these are on the screen. You can go ahead and pause there so you can draw some if you need to. I'll flip it over. You can maybe pause it, draw some if you need to. Okay, so we're going to talk about the difference between these graphs. So here are the graphs that were used to make this shape, and here's the graphs that were used to make the cardioids. So you should be noticing something here. On these ones, the amplitude and the vertical shift were exactly the same number. So the amplitude meant that you were 2 above the x-axis and 2 below the x-axis when you started. So then when you shifted up 2, your graph sat on the x-axis. And that would be the case for all of them, because the amplitude and the vertical shift were exactly the same. On all of these, our amplitude was exactly 1 smaller than our vertical shift. So if I have an amplitude of 1, that means that I'm going to be 1 above the x-axis and 1 below the x-axis. So then, when I shift up 2, that means that I'm going to be shifting up 1, which would set it equal with the x-axis, and then 1 more, which leaves a space of 1. If this had been a shift up 3, then it would have, my graph would have been up 2, and instead of divoting in at 1, my graph would have divoted in at 2, if that makes sense. Alright, so these are the things that we're going to be thinking about. So there's similarities in these graphs for sure, and then there are some things that are a little bit different. Alright, so again, we'll notice all of these, the amplitude is 1 less than the vertical shift, and that's what provided that space of 1 right there. Okay, so these are the things to keep in mind. Okay, so let's look at some of the questions that we have down there. Oh, I guess I gotta move this. So, how does determining the size, and this is called this is one I'm pretty sure I'm pronouncing wrong. This is called a limacon. I think there's an accent in there somewhere. I feel weird saying it like that. But the reason, in my head, I think these kind of look like lima beans a little bit, where they like kind of divot in on one side. So that's how I remember them. The cardioids kind of look like hearts, like cardio. And then these kind of look like lima beans, so that's how I remember it. So the size and direction would be the same as the cardioid. So the direction is still determined by whether or not it's sine or cosine, and if it says plus or minus. And then the size, how far it goes out from the center, is still determined by how big the amplitude was plus the vertical shift. So this one had an amplitude of 2, so that meant that it was 2 above the x and 2 below the x. And then when we take that 2 above the x and shift it up 3, it goes up to 5. So our size is found the exact same way as with the cardioid. And then how is this graph different from the cardioid graph? We already talked about that. That would be the cardioid goes into 0, and this graph does not go into 0. So what I would do is maybe pause the video and take a couple moments to explain the difference of why one went towards 0 and why one did not. And that has to do with the numbers that are right here in front, if they're the same or if they're different. Okay, we're going to go ahead and do the next graph. So this one you can see, again, the numbers are different, but we've switched which one is the amplitude and which one the vertical shift, which one is bigger, we shift this time. So again, we're going to call ourselves group 1. So we've got 1 plus 4 cos theta is the polar graph that we'll be doing. Go ahead and do this side. And so I'm going to go ahead and graph it in rectangular. Y equals 4 cos x plus 1. So this time I know my amplitude is 4, and then I'm going to shift it up 1, which is going to mean my graph needs to go up to 5. So there's 4 for the amplitude plus 1 for the vertical shift. And then 4 for the amplitude. One, 2, 3, 4. 1, 2, 3, 4. Okay. So cos graphs start up at 4 for amplitude of 4, end at 4, hit -4 in the middle. In between these, I'm going to cross at 0. In between those, I'm going to cross at 0. And then every point needs to be shifted up 1. So at 0, I'm up at 5. Pi fourths looks like it's at about 4. Pi halves is at 1. 3 pi fourths is about like -2.5. Pi is at -3. 5 pi fourths, might have it at -2 here. I'll go ahead and say -2.5 again. And then 1. And then about 4, and then 5. Alright, so this one starts out at 5. And then at pi fourths it goes to 4, and then at pi halves it goes to 1, and then at 3 pi fourths it goes to -2.5. So let's be careful here. 3 pi fourths is this line. -2.5 means it goes the opposite direction. 1, 2, 2.5. Okay, so let's go ahead and start drawing this curve. This has not been happening the other times. We haven't had any that were negative before. Oh gosh. Ooh. There we go. Alright, now if it went from 1 to negative 2.5, that means that somewhere between pi halves and 3 pi fourths it would have cut into 0. So what I'm going to do is I'm going to just start tapering this in. We're going to cross into 0 right here, and then I'm going to keep the curve going to follow it out here. Okay, so this one's getting a little weird. Alright, at pi, it's at negative 3. So 1, 2, 3. Keep that curve going. At 5 pi fourths, it's at negative 2.5. So I'm going to count 1, 2.5. And then at 3 pi halves, it's at 1. So right here, it's at 1, which means that to connect from here out to here, it must have crossed through 0 to then get to a positive 1. And then 7 pi fourths is at 4, and 2 pi is at 5. Okay, so these are called limacons with an inner loop. So now we want to compare with some of the other graphs that we would have seen. So I'm going to notice a few things about this graph. I'm crossing at 1 here and here. The size of my loop is 3, and then the size of my picture overall is 5. So I think at this point we can safely say that the 1 plus 4 making 5 is what determines how far out it goes, because that's the amplitude plus the vertical shift. And I think it's safe to say that this 1 has to do with the vertical shift because it's been that way every time. So now we want to compare and see what the inner loop comes from. All right. So here, and the equations are a little bit more exciting on this one. So here we have a sine graph. It's positive, which makes it go up, so that's not surprising. We cross at 1 and 1. That's not surprising because it has a 1 there. It goes all the way out to 7. That's not surprising because 1 plus 6 is 7. And then this inner loop part goes out to 5. And I'm guessing some of you guys are probably seeing already what it is. Okay, so this one right here, it goes to the right. Not surprising. Crosses at 2 and 2, so that matches that vertical shift. It goes out to 7, which makes sense. And then if you look at the size of that loop, the loop goes out towards 3. On this one, we're crossing right here at 2 and 2. The picture goes all the way out to 6, but our loop only goes out to 2. And then we've got these. So go ahead and pause so you can get your pictures drawn. Right, left, up, down, one of each. Here's some more. Alright, so what you should be noticing, I'm going to look at the rectangular graphs to talk about this, is that the negative part of the graph is what forced that inner loop to happen, right? We were going along graphing, we were coming out where we expected to be, and then because it was negative, it forced itself to be on the wrong side of the circle and kind of invert itself. So the size of the loop is how much of your graph ends up underneath the x-axis as you're graphing it. Alright, and that's going to be the difference between the amplitude and the vertical shift. So my amplitude said I was 4 above the x-axis and 4 below the x-axis. And then when I shift it vertically up 1, instead of being 4 below the x-axis, it's now 3 below the x-axis. And so that's what creates the loop that is 3. Let's maybe look at another one. Like this one had an amplitude of 4, so it was 4 above the x-axis and 4 below, and then we shifted it up 2. So that meant that the size of the loop there would have been a 2. All right, so that's what we're noticing there. So that's what determines the size of the inner loop. So now when we're comparing the equations of the cardioid, the limacon without the inner loop, the limacon with the inner loop, you want to talk about the numbers and how they affect what's happening near the origin. So you notice, and in this case, go ahead and cross out origin and put pole. We're talking about polar, so that's what it should have said. So cardioids dip in and they actually touch zero. You should be able to explain why a cardioid touches zero when a limacon without an inner loop would not ever touch zero. And why does the limacon with an inner loop touch zero but then have the inner loop? You want to be able to explain what's happening there for each of them, all right? And it has to do with the vertical shift and the amplitude. Okay. This video is the longest video of all time. So sorry. Sorry, not sorry. Okay, so for this one, I feel like I need to take a break, like I'm getting tired here. Okay, for this one, everyone did the same graph. So we're going to go ahead and do y equals 4 cos 2x. So this is telling me I've got an amplitude of 4. This is telling me that I've got a period of pi. So I'm going to go ahead and draw 4, -4. And then since I've got a period of pi, I'm going to go ahead and go out to pi halves for my 4 boxes. And pi. And I'm actually going to, even though I know that the whole excuse me, that the whole period of the graph is from 0 to pi, I still need to keep going because we're graphing in polar. That needs a whole circle. So we have to go all the way to 2 pi. Okay, so my period, it starts at 4 and it's going to end at 4. And it's going to hit -4 in the middle and then cross at 2. Or sorry, cross at 0. And then the same thing is going to happen again. Okay, so let's fill in our points. So for 0, we've got 4. For pi fourths, 0. For pi halves, -4. And then 0. And then 4. And 0. And -4. And 0. And 4. Okay. Alright, so for the first point, from when the radians are 0, we're at 1, 2, 3, 4. And then at pi fourths, somehow we get into 0. So it would be kind of helpful to know how we got from 0, from 4 out here to 0 in the middle. Is it just like a straight line that goes down? No, probably not. That'd be silly. So what I want to look at is what happens between 0 and pi fourths. And what I can see is that in between, which must have been like pi eighths or whatever, it hits 3 about. So halfway in between these, this is where pi eighths would be. And I'm going to just draw a radius of 3 right there. Alright, so this kind of helps me with my curve. Here I've got a curve out like this. Okay, now I can keep going. At pi halves, we're going to be at -4. So pi halves, 1, 2, 3, 4. And again, I probably want to see what happened in between pi fourths and pi halves, so that's right here. So in between pi fourths and pi halves, I'm going to just be consistent and say -3 here. So then counting on the other side, 1, 2, 3. And then at 3 pi fourths, we go back to 0, and I think at this point we can maybe see that we're just going to have these points of 3 in between. So at 3π4 we're back at 0. And what I just did is I made like a petal, like a flower petal. I'm going to go ahead and label this as 1. I'm going to label this as 1 so we can see the order that things are going in here. Okay. Now at pi, we're at 4. 1, 2, 3, 4. So I know that in between these, if I look between 3π4 and pi, I can see it crosses at 3. And then at 5π4 it goes back to 0. So I must have hit 3 first. And then this is my second petal. So that's that one right there. And then at 3π we're at -4. So it goes the wrong direction. So -4 and then back to 0. There's our third petal. And then for 2π, it goes back to 4. So this top, I'm going to call this petal 0 because this is like where I started half the petal. And then over here I'm going to call this petal 4. This is where I finished the fourth petal. Okay. So kind of interesting. We had a 2 theta, we ended up having 4 petals, which makes sense if you look at the picture that these kind of made 1, and then another petal, another petal, another petal. And you'll notice here that they don't go in order. It's not like you're going from 0 to 2π, so you draw the first petal, the second petal, the third petal, the fourth petal. They kind of skip around. So it starts here, goes here, goes here, goes here. Well, it kind of looks like they're going backwards order, actually. But if we were to think about the order of when we drew it, we went like this. It went around like this, and then here, and then here, and then there. So that's the pattern. So it definitely had a pattern. It kind of reminds me of like those, I don't know, when I was little I did these drawing things where you kind of like put your pencil in and it spins. Anyway, okay. We're going to do the next one. The table on this one is terrible, so we're going to ignore the table. I should have fixed that before I printed it. Go ahead and pause the video for a moment and predict the number of petals that you think this equation will have. So pause, write it down. We're going to go ahead and do an amplitude of 6 because it's more exciting looking. So the graph we're going to do is going to be 6 sine 3x. And so here the amplitude is 6 and the period would be 2π thirds. Right? Because that's how we figure out period is we do 2π divided by this number. So I'm going to go ahead and draw that 4 boxes is pi thirds, 2π thirds, pi, 4π thirds, 5π thirds, 2π. And I'm doing that. I hope you guys have noticed I like the groups of 4 just because they are easier to draw. Sine graphs actually start at 0 and end at 0. We've been doing cos this whole time. So start at 0, end at 0 for the period. They hit 0 in the middle. And then usually between the first 2 points they go up to 1 and down to -1. So we're going to go up to 6 and down to -6. And then we'll do it again. Up to 6, down to -6. Beginning and end, hit 0 in the middle, up to 6, down to -6. Alright, and then here's the values that we're going to be using are almost like straight from the unit circle, like the ones that are written there. So we're going to do 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. We're going to go by sixths. So, I don't know where to write it. Okay, 0, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 8, 9, 10, 11, 12. Whew. I don't know if you guys could tell how bad that hurt my brain. So we start at 0, and then at pi 6 we're up to 6, 0, negative 6, 0, 6, 0, negative 6, 0, 6, 0, negative 6, 0. Whew. Let's see how much I labeled. Yeah, I did them all. Alright, so I'm starting in at 0, 0, and then at pi 6 it goes out to 6. So somewhere between 0 and pi 6 I had to hit a number. So between 0 and pi 6 it looks like I've hit about 5, so I'm going to go ahead and use that to help me make my petals this time. You'll notice when I'm drawing the petals, I don't go straight down this line. I draw it curved, because these would curve. Alright, and then from pi 6 to pi thirds it's going to hit 0 again, so I'm sure it's going to hit 5 before it does that. I'm going to go ahead and label this as 1. So, first petal. Okay, and then at pi halves it goes to negative 6, down here. And if we looked at our graph in between pi thirds and pi halves, in between there would hit negative 5. And then at 2/3 it goes back to 0, so I know in between here it would have hit negative 5. So there's petal 2. On the wrong side because it dipped negative there. And then at 5 pi 6 it goes out to 6 again, so that means halfway in between it must have gone to 5. And then at pi it goes back to 0. And then at 7 pi 6, which is right here, it goes to negative 6, which is right there, and that's a point we already drew. And then it goes back to 0. So again, at 7 pi 6, we're counting the opposite direction, which is over at pi 6. That's a petal we already drew. So this is petal 4, but petal 4 and petal 1 are the same. And then next, we would have 3 pi halves, which again is a petal we already drew. So petal 2 and petal 5 are the same. And then the next one we would draw is 11 pi 6, which is in the negative direction. Again, that's petal 3. We already drew that one. So petal 6. Alright, so there are some questions for you to fill out after this, like, did the graph have as many petals as you thought it would? And the answer, I would guess, is probably not. You probably expected it to have 6 when it really only had 3 because they were on top of each other. So what I want you guys to notice is that petal 1 at pi 6 and petal 4 at 7 pi 6, those are exactly 180 degrees apart, or they're exactly pi apart. So this one was on the right side of the circle, this one was on the wrong side of the circle, so it bounced up and made it so it was on top of this one. These two are also 180 degrees apart on opposite sides of the circle. Also, pi apart on opposite sides of the circle. So the reason that we had just 3 petals instead of 6 is because the petals ended up being exactly on top of each other, which is actually what happens every time you do an odd number for the period change. And that's something that you're welcome to look into more if you would like. So every time we have an odd number here, it ends up being that the loops would be on top of each other because they're exactly 180 degrees apart, or they're exactly pi apart, and they would be on opposite sides. Alright? And then the even ones always have double the amount of petals, and the reason for that is because there's never going to be a point where we have where we have petals that are 180 degrees apart or pi apart. So that's why those double, is because they really do each represent their own petal. Right? The amplitude changing the petals, you're probably noticing that the amplitude determines how far out this loop goes, and how far out the loop goes determines the length of the petal. So that is hopefully something that you noticed. And then what difference does sine and cosine make? You'll notice that the cosine graph starts out at 4, so that means we're starting in the middle of a petal for cosine. The sine graph starts in at 0, so that means when we start the sine graph, we're starting at the very beginning of a petal. So here, if we start halfway through a petal, that means that halfway through a petal is always going to be at 0, so you're always going to have a petal through 0. On these ones, we start at 0 at the beginning of a petal. So for a sine graph, we're never going to have a petal sitting right here on the x-axis. So that's kind of a way that you guys can tell if it's sine or cosine. Whew, made it through that video.